Hello and welcome. This is an AQA A2 physics topic video. Sorry about just to rearrange the camera. Okay, so this is the second half of looking at radioactivity. Okay, so in this video, just got the plan obviously, I'm going to be giving a little bit of a recap on what we did in the last video. For those of you that obviously just can't be bothered to go back and watch the previous video, so I don't want to give too much of a detailed explanation. Obviously you can watch the proper video if you're that bothered about it. And I'm going to be looking at what carbon dating is, how we can obviously use the equation that we know already to apply it to carbon dating. Okay, and I'll give a bit of explanation why we call it carbon dating. Weirdly enough, it's to do with carbon. And then I'll be looking at traces, so the biological sense in terms of you know, the traces, the kind of iodine stuff. Okay, we're looking at that. And then I'll also be looking at the physical trace. The biological traces such as the iodine and the gamma camera. I'll be giving a bit of a cover of that. I'll be looking at the physical traces. Okay, so you've got obviously we'll be looking at leakages within pipes, even though it's more physics than it sounds. And then I'll be also just giving a quick overview of what factors make, because obviously there's varying types of radioactive substances such as uranium, technetium. Okay, and I'll be going over why you'd use a certain radioactive substance over another. Okay, because obviously they've got to choose a certain one and why. We'll also be looking at something called thickness monitoring. This is just measuring the thickness of foil, okay, and how we actually measure it and why we use a specific and only one type of radiation for that, okay. And then we'll be finishing off by looking at the nuclear radius, okay. And as I said, there's not too much that I can really talk about in that. It's just an experiment. I'll be giving an overview of the experiment that takes place, and obviously we'll be looking at an equation, and we can therefore derive the we'll be looking at the density of a nucleus, okay. And obviously I'll give a general example of a density of a nucleus, okay. So that's all to come. But the first thing I want to do is just give a quick recap, as I said, of what we did in the last video. So what we talked about was Rutherford's experiment, and in Rutherford's experiment what we said it happened was he just obviously fired a couple of few thousand alpha particles at some gold foil, and he originally thought it was a plum pudding model. So basically you had this positive jelly sort of thing and loads of little dots of electrons, okay, or negative charge. That's what they obviously knew it was. And some of them were deflected, some of them weren't, and only 1 in 1,000 were deflected more than 90 degrees, so straight back, okay. And we obviously used that to come up with an equation which was d squared, the diameter of the atom, the alpha particle, and big D squared is equal to big D squared, which we said was the diameter of the substance, okay, whatever it's being fired at, over 1,000 N, or 10,000 N, sorry, okay. So that's essentially what we said. And we come up with a couple of conclusions, obviously from his experiment, that most of the charge was concentrated at the centre and it was positive, okay. So we had a quick explanation of that. We also went on to talk about what gamma cameras, that's what I'm about to talk about. Geiger tubes, I don't remember the name for that, and that's essentially where we had a small, it's basically obviously a tube which is plugged into the mains, not literally all of it, but the outside case to give it a negative, the case of negative charge, okay. And when these electrons enter into the Geiger tube, not the electrons, the radiation, so the alpha, beta, gamma radiation enters the Geiger tube, okay. It ionizes the low pressure gas atoms that exist. Argon gas, sorry, low pressure argon gas, and obviously it ionized them, which caused more ions to flow in the anode, which was going through the centre of the Geiger tube, okay. And obviously that caused an increase in the amount of ions in the circuit, and obviously that increased the flow of electrons and ions through the circuit, which increased the current, okay. And obviously it's just worked out by the simple idea that the activity is proportional to the current. Okay, and basically the Geiger Tube uses many mathematical formulas to be able to derive, okay, well, what the exact change in current, what must that have been caused by an exact change in, you know, the activity by how much, okay? But we weren't really expected to be able to, you know, come up with any equation for that, so we didn't. And then, obviously, I went on to kind of look, well, what is alpha stopped by, what is beta stopped by, what is gamma stopped by, okay? And obviously we looked at where it deflected in a magnetic field, so it might be worth just having a little check of that. But in essence, okay, so alpha was stopped by pretty much anything, okay? Almost just stopped by, not stopped by air, but it is stopped by, can't go that far in air, okay? It is eventually stopped by air, but it needs to go a certain distance, but it can travel a little bit, so he said it is a little bit debatable, okay? Whether it does travel through air or it doesn't. I mean, in the ticky box, you think. Okay, and we said that beta was the middle in terms of ionising, okay? And gamma was the least ionising, okay? And we said that gamma is we said the more ionising a substance is, the less it can get through. So obviously alpha was the most ionising, so we said that can't get through anything. Whereas we said gamma was the least ionising, so it could get through almost anything apart from lead. Whereas beta stopped by lead and aluminium. Okay, so and we said obviously the gamma is not deflected in a magnetic field, okay? And we went to look at the cloud chamber, obviously from that intensity, which was obviously that equation where the NHF, so the energy of a photon over the area, 4 pi r squared, okay, was obviously equal to the intensity. And we kind of spoke about that. So we also then went on to look at radioactive decay and came up with a number of equations for that. Okay, so that's essentially what we did in the last video. Now moving on to this video, well obviously we're going to be looking at something called carbon dating, which is basically, we're looking at the activity, you will hear this tossed around when people are talking about, well, how old is something, and we're trying to work out, you know, if it's been dead for thousands of years or just 5 years. I mean obviously, you know, if it's a body, you're like, well, that guy looks pretty dead to me. You probably tell how long it's been, in forensic stuff. But carbon dating is obviously the main thing the best thing to sort of explain it with is plants and trees, that kind of thing, okay? Now, obviously, you're smart enough people to realise that, obviously, plants, trees go through photosynthesis, which is basically, it takes in some carbon, because obviously carbon in the atmosphere reacts with the nitrogen, okay, and it's taken in by the plants and the trees, but they also give it out when, you know, when they're dying. They don't always keep all of it, okay, so they have quite a constant level of activity, okay, because this is radioactive, some of it decays, but therefore, you know, some of it is constant, but then when it dies, obviously it's not taking any in anymore, but because it's dying, it's slowly decaying, so therefore we can say, well, you know, it starts to reduce its activity. Now, what we came up with, and we said in the last video, the equation for the activity was the activity that you want to register, okay, is equal to the initial activity times e to the power of lambda t. Okay, so I'm assuming that is all familiar. Okay, and basically carbon dating is using, it's sort of going backwards, so in carbon dating we would have the current activity, okay, so that's obviously the current activity of the dead substance you're measuring, whereas A0 is the initial activity, and obviously the initial activity would be the activity when the tree or whatever it is was live, okay, so you would obviously just get the same kind of, not necessarily the same kind of species, it wouldn't have to be, but something that is fairly similar, okay, and you would obviously work back by ln in both sides, natural log in, taking the natural log, and obviously hopefully you'll be able to work out the decay constant, work out the decay constant if you're not already given it, okay, and obviously therefore you would just work backwards and find the value for t. Okay, and obviously t is generally given in years. Okay, so that's pretty much how far carbon dating goes. Okay, and that's really the equation that goes with it. Now what we're going to be looking at next is just something called traces. Okay, now obviously it's not one, we're not talking about them in the context that, you know, you get followed around and people go, hey, I traced you down, you need to stop being a reckless teenager. I'm watching Bill's 7187 YouTube videos, which you turn around and go, no, I can be a rebellious kid and waste my life if I want to. Don't need someone telling me not to. So that kind of thing. It's not that, don't worry. Okay, so traces, what we mean by that as well, there's obviously two types, as I mentioned at the start of this video. So we've got the biological type, which is the iodine, you know, the barium meal that you, obviously, you don't know if you had it, but where they look at your digestive system, okay? So basically what happens is, obviously you have this meal and then they look through cameras, okay, and they will pick up where it is. And well, say I probably shouldn't have picked the barium meal to try to describe, because the gamma camera is a better example of something like that. Okay, but really they can see, you know, where is it going? Is it acting in both kidneys? Are both kidneys trying to great, I'm losing my words today. Sorry. Both kidneys functioning properly, you know, breaking it down in the right way is what I'm trying to say. Okay, so obviously they can compare that. But the one I was trying to mention then, but I just kept interrupting myself, was the gamma camera. Okay, I was going to embarrass myself and draw a skeleton on the board. Okay, which is a rubbish little thing. I don't know. Yeah, this isn't going to go well, is it? Alright, okay. Let's see. Right, I'm going to try and attempt this now. Okay. Obviously, this is how everyone looks in the world. So this is how we're all going to look under a gamma camera. So, you know. You can tell I didn't take heart. Anyway, okay. So basically, gamma camera is essentially when obviously someone takes in consumes a radioactive substance which is a gamma emitter. Okay, and that is often technetium-99, and we'll go into why it's technetium-99 when we go on to why do they use certain substances. Okay, so it's labelled TC and 99 as the atomic number, atomic mass number. Okay, so that's another thing we're going to come on to in a second. Right, and basically there's a meal which is technetium and calcium, okay, or it might be drink or something, and basically the technetium is the gamma emitter, okay, and obviously calcium goes to the bones, obviously for growth, etc. Now obviously if we were looking at teenage boys, which is myself, it would be the ends of the bones where you would see growth, okay? Now obviously, no, you don't get to 40 and you go, oh, I've got another limb growing on my arm. Obviously, you know, it's more pronounced in, obviously, teenagers, okay? So really you would see you would expect to see, so the bones, the general sort of, the distant, you know, the actual bone wouldn't be lit up, but it's a joint sort of thing, okay, where the bones grow out from. They are, obviously, the calcium is absorbed by that, but it also helps to detect, you know, obviously, if you've got any cancer, cancerous bowel cancer, for example, okay, you would obviously see, because obviously that has to grow, so it needs calcium, so you would see, you know, a dark spot maybe in the sort of the pelvis kind of region, okay, where, you know, that would indicate cancer if, you know, if it was there, obviously. Okay, so that's kind of what gamma cameras are. Okay, it would just be a gamma detector or a gamma camera, okay, is more commonly known, and that would obviously pick up where it's been emitted from, and obviously the darkest bit is where, because obviously it's been teamed with calcium. Okay, so the technetium is just showing the gamma camera where the calcium is being absorbed. Okay, so that's one of the uses of it as well. Right. there's anything else. Oh yeah, one more thing. Okay, so say we've got this, there's another, I mean there are loads of traces, but the two main that I'm going to mention are obviously the gamma camera, and then we're going to look at this sort of leakages, okay, and blockages even. Alright, so say we've got this pipe, this obviously very advanced pipe here, and at this end of it we're going to put this radioactive source, okay, which is obviously going to be a gamma emitter, and we're going to send it through, okay, so hopefully it's not a water supply, but as I said we'll come on to something like that in a minute, and right, and it's going to emit gamma, okay, but obviously if it's a lead tube it's not going to get through, but when, yeah, get through, okay, but if we've got, you know, a leakage, okay, and obviously we've got lots of gamma coming out, when you pass a detector up and down this, you will see obviously a spike or some kind of increase in the readings, okay, you know, if there's no other obviously activity, you'll only see the activity where we've got this leakage, and it helps to pinpoint it down, okay, and obviously you can narrow your search down and it will highlight where the radiation is being escaping, sorry, okay, so essentially that's what this tracer does, and obviously it will decay after a while because of the half-life, okay, but now this leads us on to what obviously our next point, you know, it's not going to lead us on to our last point, I'm going to go back in time for you. Tracers, obviously, as I said, I would refer to it at this stage when I was talking about technetium, and I said, well, they choose technetium, and obviously they don't just pick it because, well, it's radioactive, I don't care if it kills the person, as long as we can see where his cancer is, you know, it doesn't matter if this radioactive poison kills him, or broken bones, it doesn't matter, we need to see where his bones are broken, it doesn't matter if he dies, as long as we know he's got a broken leg, we can sort that. I mean, death is, you know, irreversible, but, you know, as long as we know he's got a broken arm, we can fix that. Obviously, one of the main points, okay, about what makes them, you know, pick a certain radioactive substance over another, to kind of set it straight away there is, well, is it toxic? And you could apply that to this as well, because if we're passing, you know, a radioactive substance through the water supply, unless it can be filtered out easily and quickly, or if it's not toxic, then you know, they wouldn't pass it through. Right, so is it toxic? Now the next one is sort of the half-life of it, or the existence of it. Okay, so the half-life. How long is the half-life? And we say that because, well, obviously you don't want it to be too long, but then again we don't want it to be too short. Okay, now technetium I think has got a half-life of around 60 minutes or seconds or something. Not very long. Okay. Has it? I might be wrong on that, but basically, I think it's 8 days. Yeah, I will correct myself if I'm wrong. I'll put a little thing on. But I think technetium has a half-life of around 8 days. Obviously, you can research it. But as I said, that's my thing. I don't know why I said 60 seconds. I think I'm thinking of something else. Okay. So anyway, obviously it takes 8 days for the study to go through. Okay. So obviously they need it for a certain amount of time. They don't want it any longer because obviously radioactive sources are dangerous, and obviously they do decay. They don't just decay themselves. Obviously they, you know, pass on products and stuff, and it's not good. Okay, so we only really want it there for as long as we have to have it there. Okay. So that's one of the things of the half-life. Now the next one, well, does it decay into? So what about the products? What are the products like? Okay. Obviously, if it decays and it decays into something else, then it decays into something else, then that decays into something else as well. Obviously, that's going to increase the life of that substance is there. But if it's decaying into products which aren't stable, okay, it's obviously going to become quite dangerous, because obviously if that mixed with certain other things, and you never know what, obviously you do know what it could create, but yeah, if it's not going to be a stable product, what it creates, what it decays into, okay, so that's going to be quite dangerous for a couple of reasons. So they're really the three main points that you would talk about. You might get a 6-marker question on, you know, why do certain radioactive substances are picked, okay? And you might specify technetium for the gamma camera, okay? And obviously you could explain what the gamma camera was and relate it to each one of them points, which if you were to do that, obviously it's not going to be toxic, because obviously otherwise it wouldn't be ingested, okay? So it needs to be consumed, so it obviously can't be toxic, and obviously the half-life is only going to cover, sorry, I don't know what's so we've got a bit of a bad throat, but you know, diseases can't come through the camera, they haven't invented that yet, so you're alright. Okay, so the half-life is only it only exists for as long as it's needed, okay? So the half-life is exactly right, and obviously it doesn't decay into any unstable products, okay? So therefore it can be used in this situation. Alright, now the next thing we're going to go on to is something called thickness monitoring. Now this is not something how you describe your friend sitting next to you at the table in physics and go, how thick are you? Let's measure that. I saw it on a revision video that I was watching, okay? That my parents or some teacher or someone forced me to watch, okay? So why not use his advice and measure someone's thickness? Okay, now obviously we're not talking about that kind of thickness, otherwise I'd be a lot more worried about measuring myself. Okay, so essentially the sketch that you would draw to kind of explain this is, obviously we've got, you know, a sheet of metal, and then you will have two rollers. As I said, this looks really weird and I do apologise. Basically you will have two rollers, okay, and they will create this thin sheet of metal, okay, and you will have a radioactive source and a detector, okay, and detector and source, and obviously you can adjust the rollers to alter the thickness of this thin sheet of metal. Okay, now what radiation would we use for this? Well, we need to go back to the idea of, okay, what would pass through it? Well, we know for a kick-off that obviously alpha, it wouldn't really pass through paper, so it's not going to pass through foil. So we couldn't use alpha, and we couldn't use gamma either, because that passes through pretty much everything, okay? So we could use gamma in the essence, well, it does get through, but we could make that really, really thin. We could remove the rollers altogether and it would still give us exactly the same reading, and as if we made that ridiculously thin, okay? So we couldn't use gamma, so therefore we have to use beta, because beta is sub halfway between gamma and alpha, okay, which is perfect, because you know, certain thicknesses it won't go through, certain thicknesses it will, so obviously you can vary between, and it varies sort of linearly between you know, the amount, the thickness of this foil, okay, and the amount of obviously particles that it emits, you know, that are emitted, that which are scattered or don't go through at all. Okay, so that's really thickness monitoring, and why we use beta and not alpha or gamma. Alright, so that's pretty much the explanation for that. Now what we're going to go on to now is something called the nuclear radius. Okay, now this kind of almost requires you to have a little bit of an understanding again of diffraction, okay? So I mean, mostly it's your single slit diffraction, okay? So when we looked at single slit diffraction, we were talking about zero order beams, the first order beam, and the second and third, however many that you would have, okay? And we said, you know, that was when there was constructive interference, when you saw a bright light, say you weren't dying, although in a physics lesson you probably were losing the will to live, but hopefully that bright light wasn't the sign of you dying, it was a sign of an interference pattern, okay? Right, okay, so really that was just looking at the zero order beam, just will always be twice as wide as the first order beam, because you know you've got the two imposing on each other. As I said, there was a AS video on that, so do check it out, but hoping that was a little bit of a refresh. Okay, and what we had in that single slit was we had a light beam. Obviously I'm not going to draw the light box because we're talking about nuclear radius and I need to kind of relate it to actually something A2 level. Okay, and we had a single slit and it went through. But obviously we're firing electrons at this, okay? And what we want here is we have this detector, okay? And it will go through and it will... We are looking where it will hit the detector, okay? And we're going to put the detector at some angle to the normal. Okay, so obviously it might go over here, wherever. We're looking at how many particles are deflected at the angle which the detector is, okay? And basically what we're looking at there is the angle, so we can work out the de Broglie wavelength, okay, which is your lambda, or your de Broglie wavelength is Planck's constant over the mass times the velocity. Alright, so that's pretty much the wavelength. Okay, so the detector is used to measure the number of electrons per second diffracted through different angles. Okay, so it's high energy electron diffraction because these electrons that are coming in are at a very high velocity. Okay, and obviously because we're going to be using sine theta to work out obviously the varying number of electrons, okay, that have been obviously diffracted, we would use obviously we just come up with this graph, okay, we get this from the table of results and the detector reading, okay, so if you were to move the detector, say, through different angles, okay, you would end up, say this is the angle, okay, so we're looking at theta on the x-axis and the detector, okay, so the number of counts per second, and the graph would look something like this, okay, and that's obviously because you would have like sine 90, which is 1 and different, basically it's sort of like the sine graph, you could almost imagine it like that. Okay, so that's pretty much the typical results that you would get, and the graph shows that the angle theta to the detector 0 order beam is increased, sorry, the angle theta of the detector to the 0 order beam is increased, the number of electrons per second decreases. Okay, so basically what I was trying to specify there is the greater we make this angle, so the more we move it either side, okay, of the normal, the less that we see, okay, because see less electrons are diffracted by a greater angle, okay, so there's a lot that are, the most is just directly, if you were to put the detector at n, okay, on the normal line, you would receive the most amount of electrons because obviously only a few are going to be diffracted. Okay, it follows the Rutherford experiment idea where we had 1 in 1,000 or 10,000, 1 in 1,000 n. Okay, that were deflected by more than 90 degrees. Okay, so it kind of follows that idea. All right. So that's the nuclear radius. Now the nuclear density. The nuclear radius is just one. Basically, we just come up with this formula, and it's something that you just sort of need to know. Alright, and the radius, the nuclear radius, is equal to the R, is equal to R0 times A to the power of a third. Now, I'll just explain what the individual terms mean. Okay, so this R0 is just sort of like a radius constant, okay, which is 1.05 femtometers, or in other words, 1.05 times 10 to the minus 15 meters, okay? And basically that's just like Planck's constant we have over here, but because obviously the radius, the nuclear radius, because obviously they have nucleuses of different atoms have sort of, you can assume it to have a varying constant, okay? So we've just come up with this. As I said, I will do another video on that if needs be, but I'm assuming that is okay. Now that's why it's a little bit confusing, because you might go, oh, well, that's the initial radius and then that's the radius, and how could we change the radius, okay? Well, you can't, obviously. The A is not the area, it's actually the mass number. Okay, so that's just the atomic mass number, okay? And if that's the atomic mass number, now the best way to, I probably should explain something at this point, okay? So how do we actually calculate the atomic mass number? Okay, obviously you can look at the top, you know, when you see, we go back to the technetium, okay, that 99, that is represented by this A. That's what we mean by the mass number, okay, so that's essentially where we're coming from. Right, but there is a formula, okay, so, what's that, sorry, so if that's the atomic mass number, okay, basically that's the number of nucleons in there. When we want to work out the mass of the substance, okay, just the raw mass is equal to AU, okay, so the A is obviously the atomic mass number, and this U represents the atomic mass unit, which is a 12th of the mass of a carbon atom, okay, so obviously a mass, you know, the atomic number of carbon is 12, okay, so if you work out the mass, obviously that's 12 times a 12th of the mass of carbon, which get you a mass of carbon, okay? And you just apply that because it's sort of quite a common element, really. You just apply that to different eventualities because obviously we're looking at the radius here. So, as I said, hopefully, I think we just need to be able to understand that. If I do get a better understanding, I will do another video, but that's kind of where I understand it from. So if it doesn't work for you, then, well, you get stuffed. Okay, so anyway, this U, as I said, is a 12th of the mass of carbon, which if you work it out is approximately 1. So just put the side, U is 1.66, 1 times 10 to the minus 27, okay? So it's almost the mass of the proton. Yeah, it's almost the mass of the proton, okay? So that's where we've got that number from, and you can see why you just apply it, okay? Alright, now what we're going to use this for is to be able to go and explain the, so that's the nuclear radius, that's really all you need to know for the nuclear radius. We're going to go on to the nuclear density using this mass idea now, okay, so try to link it in. Now obviously the density of the nucleus, sorry I'm trying to move out of the way here. The nuclear, obviously I want to sit down as well. You know, you should know that the density is equal to the mass over the volume. Okay, well I know this is the atomic, the mass of the substance. Okay, so if we put that in, okay, so we just put this into the mass. Therefore that's AU. Okay, but what is the volume? Okay, well you should know the volume of a sphere. Therefore the volume of the because we assume that, you know, the atom to be spheres, whatever, we assume that to be volume is equal to 4/3 pi r cubed, okay? Now, well, this is the formula for the radius, okay? So you just sub that formula into r, okay, for the volume. So if you were to simplify it down, you would get the volume is equal to 4/3 pi times r0 a to the power of a third, okay, all cubed. So therefore that would leave you with the volume is equal to 4/3 pi times r0 cubed times 8, because obviously something cubed root, which is essentially what a power to the third is, cubed, okay, that does the times out the powers, so it leaves you the power of 1. So really we could write that as a to the power of 1, or in other words, just a. So you would sub that in, okay, to the volume, and you can quite clearly see if you do 4/3 pi r0 cubed a into that equation, obviously the a's would cancel, so therefore you'd be left with u over 4/3 pi r0 cubed. Okay, and you would sub in a typical value for r0, okay, which might be approximately 1.05 times 10 to the minus 15, okay, which would obviously get you around 3.4 times 10 to the 17 kilogram per meter cubed. Okay, so that's essentially a typical density of a nucleus. So you can put that in that formula, but really that's kind of a formula you just need to be able to understand. Alright, so that's pretty much it for nuclear radioactivity. So just to go over give you a brief overview of the whole topic before my voice completely goes. Okay, so at the start of this topic we looked at Rutherford's experiment, and we talked about the original plum pudding model of the atom, okay, and obviously how that was disproved. And we went on to talk about, what conclusions did he draw, which was the fact that that most of the mass was concentrated at the centre of the atom, and obviously that it was positive, okay. Then we went on to look at the Geiger Tube, which we said was just where the just lets radiation in, which ionises, causes an increase in the current, okay, which obviously leads to, because we know activity is proportional to current, the Geiger Tube works out the actual change in current, relates it to the change in activity, okay, by being it proportional, and obviously simplifying down, calculating the current. But as I said, you don't need to know that. Well, obviously you do need to know that, but otherwise I won't be mentioning it. But you don't need to know actually the maths behind it, I don't think. I'll put a big thing on YouTube over my head now saying, what a complete idiot, don't listen to this guy. You're probably not anyway if you were going to listen to that. Okay, and then obviously we looked at the types of radiation, but really kind of already mentioned that, what it's stopped by, which is the most ionising, and we just said the more ionising the radioactive sources, the less it can get through. So obviously the main example of this is that alpha is the most ionising, okay, and it can't get through that much. And if you were to bring up an example, obviously you would bring up the Russian spy, okay. Okay, so that's pretty much sort of the. Oh yeah, we went on to look at the intensity, which we said was basically the inverse square law of radiation, which was the NHF over 4 pi r 0 cubed. Okay, and we went on then to talk about radioactive decay, which we said was exponential because there's a half-life. It's the same. Okay, so it's a half of the time it takes to get to half its mass, okay, if you half that again, obviously there's a different amount it's reduced by, but it takes the same time because it has the same half-life. Okay, and then we went on to look at carbon dating, obviously in the start of this video, and we just mentioned that was looking at the activity of a dead plant compared to the activity of a living one, and using the equation A, the activity is equal to the initial activity times the e to the power of negative lambda t, lambda being the decay constant and t being the time in years. Okay, then we went on to look at traces, okay, which were, obviously we looked at the biological traces, we looked at, so obviously that was to do with the gamma camera, which obviously showed growth because we put it in calcium, calcium, and it showed growth, and the technetium was a beta emitter, okay. And obviously we also looked at the actual physical traces, so we looked at sort of the pipes, the leakages within pipes and how to detect that, and then once we'd gone over all the traces we went on to say, well, yeah, but why would they want one radioactive substance over another? And we just said 3 points for that. Essentially were, is it going to decay into stable products, is it toxic, and is it the half-life long enough for the substance to actually, be worthful, okay, so be useful in the experiment, or is it, going to last forever, okay, because obviously we don't want to use something that lasts far too long and could cause future problems. Alright, and then we looked at thickness monitoring, which was just, altering the thickness of a sheet of metal and putting beta radiation, and not gamma, because gamma wouldn't really be affected by the thickness and alpha wouldn't get through at all, okay? So that's why we'd use beta, and kind of, obviously that was the reason for that. And then we looked at what we've just done there is the nuclear radius, okay? And we said, well, we use high energy electron diffraction to kind of explain this formula, okay? Which actually, the nuclear radius is equal to the just a constant, okay, which is 1.05 centimetres, which is, because 1 centimetre equals 10 to the 15 of a metre, is 1.05 times 10 to the minus 15 of a metre. Okay, and I kind of showed you the graph for the electron diffraction, okay, explaining the Broglie wavelength again, and then we went on to look at the nuclear density, which is just applying this R formula, okay, and working out the mass, which we know was the atomic mass, which is the 99, times the atomic mass number, which we said was a 12th of the mass of carbon, okay, to work out 1 unit of mass, okay, just the element they decided to use, and applying it to the mass over volume formula from the density, cancelling out the A's, and you could just sub in a value. Oh, sorry, this R0 is not the radius. Okay, remember this is the 1.05 centimetres, so if you did pay attention throughout this video, well, actually, I corrected myself. It's a good job I continued with this video, actually. Alright, so that's what we looked at. See, this covers nuclear radiation and radioactivity. What we're going to go on to look at in our next video for physics is we're going to look at, obviously, the Einstein's famous equation, E equals mc squared. So we're not going to go into too much of relativity, even though I would like to, but it's not really part of this course. Okay, and we're going to go and look at something called the mass defect, okay, which is it's just essentially the difference between the mass of the products and the mass of the actual atom, okay, and the mass of the atom combined is less than the individual mass of the products if you were to add it up, okay, so that's a little bit into the next video. Okay, and we're also going to look at binding energy, which is actually the opposite of what you think it is, okay, and then we're going to have a quick recap and sort of extension on what we mean by fission and fusion, and we're just going to finish that off then by talking about critical mass. So it's a little bit into the next video as well, but as I said, you know, that's all for next time. So thanks for watching. Hopefully you've been able to actually hear me and my voice hasn't completely gone just yet, even though, you know, trying to kill myself, trying to get myself out for these exams. Okay, so that's nuclear radioactivity covered. Let's say if you have any questions on that, please do let me know, and I'll be trying to upload past paper questions on the topics and past papers before the exam, and if I don't, that'll be over the summer, but it'll be pointless for all of you because you'll have done your exams by then, and so will I, but you know, crazy kid, can do whatever I want. Alright, so thanks for watching, and hopefully we'll see you in the next video.